So, hello all. Let us have a very quick recap of what we learned in the last lecture. So, we learned that a molecule, apart from having electronic levels also has vibrational levels, and these vibrational levels are quantized, and the vibrational energy EV is given by V plus half into h nu, where V is the vibrational quantum number, and this vibrational quantum number can assume integer values starting from 0, 1, 2, and so on. Nu is the frequency of vibration, and this is given by nu is equal to 1 by 2 pi under root k by n, that of a simple harmonic oscillator, and this k is the spring constant, basically the strength of the spring constant of the bond between the two atoms. The mass m is the reduced mass. We had considered a diatomic molecule, and therefore this will be equal to m1 plus m2 upon m1 plus m2. So as long as these vibrational levels are follow the simple harmonic motion, then we have seen that these energy levels are equispaced. So, and the separation between two vibrational energy levels should be constant and should be equal to h nu. However, as the vibrational quantum increases, that means the molecule starts oscillating very vigorously, then the vibration deviates from being simple harmonic to anharmonicity, and therefore the energy levels start getting closer. So, as in a real molecule, therefore, the vibrational energy levels are not really equidistant, but because of anharmonicity, they start getting closer as the vibrational quantum increases. Now, coming to the rotational levels, we also saw that molecule consisting, once again, we had considered a diatomic molecule, and which is separated by a bond length r, and we assume that this is a rigid rotor, that means this bond length doesn't change, and from here we also got the rotational energy levels, which are also quantized. As we saw here, this is a mass Na, Nb. Nb is a larger mass. Therefore, the center of mass about which this rotation is taking place, this is closer to the larger mass. Now, the center of mass we know is given by the relation MA-RA is equal to MB-RB, where RA plus RB is the bond length. Right? So the moment of inertia we had learned is given by MA-RA square plus MB-RB square, which can be rewritten in the form of equal to mu r square, where once again mu is the reduced mass, where we are considering this two-body problem into a single body problem as shown here. So this is the reduced mass, which is equal to mu, and it is at a separation of r, that is the bond length, from the center of mass. So this, therefore, the rotational energy levels, we can say ER is equal to half I into omega square, where I is the moment of inertia and omega is the angular velocity. Now, angular velocity has a relationship with the angular momentum. We know L is equal to I into omega, where omega is the moment of inertia, omega is the angular velocity, and L is the angular momentum. Angular momentum of these rotational levels is quantized, and therefore so is the rotational energy, and therefore ER, when you substitute L here, becomes 1 by 2I into L square. Now L is quantized, so L can be rewritten as 1 by 2I J into J plus 1 H cross square, where H cross is actually H upon 2 pi. So H by 2 pi whole square. So this can be rewritten as H square upon 8 pi square I J into J plus 1, where J is the rotational quantum number, and this also takes integer values starting from 0, 1, 2, and so on. So this constant, which is h square upon 8 pi square I, this is called the rotational constant of the molecule, and this is given as B. So B is equal to h square upon 8 pi square I. So the rotational energy B is J into J plus 1. So as the rotational quantum number increases, the rotational energy also increases. That means the molecule, the angular velocity increases and the molecule rotates much more vigorously. Now let us see what is the spacing between two rotational levels. We have seen that E rotational is B into J into J plus 1. So if we consider Ej, if we try to find the difference between Ej plus 1 and Ej, then it will be, this is equal to B can be already a constant. So J plus 1 into J plus 2 minus J into J plus 1. And you can easily simplify it and it becomes B J plus 1 into so that is 2B J plus 1. So the difference between two rotational levels is therefore it increases with increasing J. Unlike vibrational energy levels, we now see here that the rotational levels, as we are seeing here for J equal to 1, J equal to 2, J is equal to 3, they are not equidistant. And that is not because of any inharmonicity or anything, but the fact that your rotational energy is proportional to the value of J, and therefore as J value increases, this keeps increasing. So here we can actually calculate for J equal to 0, the rotational energy ER is 0 because it is Bj into J plus 1. For J equal to 1, you see ER is equal to B 2 into 1. So it is 2B, right? Is it correct? When J is equal to 1, it is B 1 into 1 plus 1. Yeah, so that is 2B. Similarly, as you go up and up, for J is equal to 2, it becomes B 2 into 2 plus 1, 3. So that is equal to 6B. So you can see that the separation between the rotational levels is constantly increasing. And that spacing is given by 2J plus 1. Now, one important thing that we have assumed while we were deriving this is that this is a rigid rotor. That means the separation between the molecule, between the two atoms of the molecule, this R, is it does not change. It always remains equal to R. But actually, as the J value keeps on increasing, this centrifugal force becomes so large that this R tends to increase. So when this R tends to increase, then you know that this B, what is B? B is square upon 8 pi square I. So it has this I term in the denominator. So this I is nothing but mu into R square, where R is the bond length. So when this bond length increases, I increases, and therefore B reduces. So when B reduces, the spacing also tends to reduce. But actually, anyway, it is increasing. There will be a reduction because of this centrifugal distortion. Okay. So now we have sort of read about what are vibrational levels. We also have seen that you have rotational levels, and so we are now in a position basically to understand what are Ro-Vibrational transitions, vibrational rotational transitions, or rotational vibrational transitions as they are called. At the first glance, this may appear a little confusing. So let us just deal with it part by part. Now, what we have seen is that you have the electronic energy levels, that is, which are very far apart. This is the ground electronic level in case of a molecule. And in the ground electronic level, we have the vibrational levels, which tend to get closer as you go up. Okay. And you can see that E vibration is much less than E electronic. That means the energy involved in electronic transition is much larger than the vibrational energy. And now when we consider each vibrational level, suppose this is the ground vibrational level, then in the ground vibrational level, you have several rotational levels. So let this be the first J equal to 0. Then you have J equal to 1, J equal to 2. So we are seeing that this spacing keeps on increasing. You have J equal to 4. So this is in the first vibrational level, or it is in the ground vibrational level also. See, you have these rotational levels starting from the ground vibrational level. So in the ground vibrational level, you have all these levels, which are the rotational levels, and the next vibrational level. So here now we are talking about vibrational level. So if this is the first excited state, then it will also have its own rotational level scheme. And as you can see now here, there's that in each vibrational level, you have these rotational levels fixed, and therefore E vibration is much less than E electronic, but E rotational is also much less than E vibrational. So the energy that is required to cause rotation is much less than what is required to cause vibration, which is much less than what is required to cause electronic transition. Now, having understood this, let us also just try to see that if we have a molecule in the ground vibrational state, say, and we have several vibrational levels. Okay. Now, when this molecule is inundated with, say, photons, such that the photon energy, suppose it satisfies, it is of this energy. So then, is it possible for this molecule, which is in the ground vibrational state, to go to the this V equal to 1, V equal to 2? Is it possible for it to go into the V equal to 2 state? Here, we come across what are known as, in spectroscopy, selection rules. There are certain selection rules which forbid certain transitions and which allow certain transitions. We will not go much deeper into why this happens, but at this point, let us understand that the selection rule for vibrational transitions is delta V is equal to plus minus 1. That means this is not allowed. The molecule can go from V is equal to 0 to V equal to 1, or it can go from V equal to 1 to V equal to 2, where delta V is equal to plus 1. Or it can go, so it can continue in this ladder where delta V becomes 1, or it can come down from V equal to 2 to V equal to 1, where delta V now is minus 1. So this is also allowed, or it can come down from V equal to 1 to V equal to 0, where delta V once again is minus 1. So the selection rule says that for a vibrational transition to occur, the change in vibrational quantum number should be plus minus 1. For other kind of, when delta V is not equal to 1, will there be at all never any transition? Well, the probability is much smaller as compared to this. Now, do we have also any selection rules for rotational transitions? Because rotational levels are also there, and then we have population. So is it possible that we can have transitions among rotational levels? Yes. So if these are the rotational levels, J equal to 0, J equal to 1, J equal to 2, J equal to 3, and J equal to 4, and so on, suppose, then the selection rule for rotational transitions is that delta J should be equal to 0 or plus minus 1. So now here, if we just consider the rotational levels of one vibrational state, then delta J equal to 0 is not possible. However, from 0 to 1, if suppose there is a transition, then this is delta J equal to plus 1. From J equal to 1 to J equal to 2 is delta J is equal to plus 1. From J equal to 3 to J equal to 2, delta J is minus 1. So these are called pure rotational transitions. In spectroscopic terms, these are called pure rotational transitions because these are happening in the same ground vibrational state. Now, if we consider, suppose I just try to erase this, give me a moment. Okay, now let us consider rotational transitions need not be in the same vibrational level. They can be between two vibrational levels also. For example, now let this be the ground vibrational state. Let this be the upper vibrational state. So V equal to 1, V equal to 0. And we know that this is populated by its own rotational levels. Let us not concentrate on the separation because it is just, I have just drawn for the sake of understanding. Okay, so you have now these rotational levels, J equal to 0, J equal to 1, J equal to 2, J equal to 3, J equal to 4, etc. Similarly, here too you have J equal to 1, J equal to 2, J equal to 3, J equal to 4. Now, suppose there is a transition from J equal to 1 to J equal to 0. J equal to 1 to J equal to 0, then here delta J is equal to 1 to 0 is minus 1, which is an allowed transition. Between two vibrational levels, you can also have delta J equal to 0 from 1 to 1. When we show upward arrow, then it is absorption. When it is downward arrow, it is an emission. That means the atom or molecule which is in the upper vibrational level and occupying this rotational energy is actually coming down to the lower vibrational level, but the same J value. And so delta J is equal to 0. So in this manner, one can have transitions between two vibrational levels and the rotational levels that are populating these vibrational levels. So this is these transitions are called Ro-Vibrational transitions. Okay. Now, will all molecules give rise to this infrared spectrum, pure rotational spectrum, or rotational vibrational spectrum? These are called infrared vibration. This is called infrared spectrum because the vibrational transitions, they generally fall in the mid-IR region, while these rotational transitions, they fall in the far infrared region because as you can see, the energy difference is much smaller as compared to this between VV, between two vibrational levels. So this fall in the infrared region, and therefore this is called an infrared spectrum. So whether all molecules show a rotational vibrational spectra? No. Again, there are some spectroscopic considerations, certain requirements on the molecule. For example, if we take nitrogen, nitrogen is a homonuclear diatomic molecule. It has vibrational levels. Let these be the vibrational levels of molecule, but it cannot show any infrared vibrational spectrum because the requirement is that there should be a change in dipole moment when there is a vibrational transition. Or to show a pure rotational spectrum, the molecule should have a permanent dipole moment. Why these are? Well, I think if you think a little, you may be able to understand, but at this point, these are not very important. Suffice it to say that this infrared spectrum, when certain molecules are able to show this spectrum. So now we come back to the vibrational rotational transitions. So the selection rules we have shown are for vibrational transition, as I just explained, is plus minus 1. For rotational transition, delta J is 0 or plus minus 1. So now let us consider what I show here is the ground vibrational state and the first excited vibrational state. This is all in the ground electronic level. We are not going to the higher excited electronic level. So it is in the ground electronic state, and we have the first ground vibrational state and the first excited state. Then suppose this molecule is in J equal to 0 in the ground vibrational state, then and it is shown with photons which can take it from here to here, J equal to 0 of the first excited vibrational state. Then it can absorb and go to the upper. Similarly, a molecule which is in J equal to 1 state can go to J equal to 1 of the upper vibrational level. Delta J is equal to 0. Similarly, one in J equal to 2 can go to J equal to 2 here, right? So here also, so here also the delta J is equal to 0. Now, would we expect that all these frequencies that we are trying to show, this or this or this, should not they be equal? Should not the same photon be required to excite the molecule from J is equal to 0 to J is equal to 0 of the next, or J equal to 1 to J equal to 1? Isn't it? Because as you can see, the energy difference is same, but it does not happen like that. And why? We already know that these energy levels are slightly shifted because of the anharmonicity as well as centrifugal distortion in the rotational levels. So, although we expect that all of these should come at the same frequency, there is a slight spread. The spread is not much because originally they are supposed to be of the same energy, but at this point, because of centrifugal distortion or anharmonicity, these energy levels are slightly different. Then they are not equispaced, and therefore you have a small spread. And this delta J equal to 0 is called the Q branch. So Q branch is very, very sharp. I hope you have understood why the Q branch is sharp. If you try to see what is the energy level separation between various rotational levels, you will understand that it is sharp because basically the energy is equal, but slight change happens because of the distortions, okay, and anharmonicity. Now we come to the right side of the figure. Here we are telling that delta J is equal to plus 1. That means the molecule is going from, say, J equal to 1 to J equal to 2, or J equal to 0 to J equal to 1. So you know that the rotational level spacing is increasing upward. So energy required for the excitation from J is equal to 0 to 1 is less than that is required for exciting from J equal to 1 to J equal to 2, which is further less from J equal to 2 to J equal to 3. That is because of the increasing rotational energy gap. We are going from lower rotational level to a higher rotational level. And therefore, this, you can see, they are not like Q branch. That means it is not, spread is not so small. That is because this gap is continuously increasing as you go up and up. So you have these various transitions require various frequencies. And this, when delta J is equal to plus 1, it is called the R branch in absorption. Same thing can also happen for emission that you can think later. But right now, let us concentrate on absorption. When delta J is equal to minus 1, it is emission. When delta J is equal to plus 1, it is absorption for these transitions. Now let us come to this side, that is the left side of it, where delta J is equal to -1. Now you see we have these rotational levels, and delta J is equal to -1 can also happen in absorption when from J equal to 1 it goes down to J equal to 0. So here now the delta J is -1. So we are going from a higher level to a lower J level, from a higher J level to a lower J level. And therefore, the energy separation is going to be less as compared to the R branch. This is quite obvious even when you actually draw it to scale or from the formula that we have derived. So this P branch, this is called P branch when delta G is equal to -1, and these energy levels or the energy required for these transitions is less than the Q branch, which is in turn less than the R branch. So now we have understood how there are vibrational rotational transitions, right? Now, at this point, I would just like to say that these vibrational rotational transitions are considered to be the fingerprint of a molecule. Why so? Because each molecule will have its own frequency of oscillation, the nu, whatever we said. This is dependent on the molecule. So is the rotational energy level, which is also B J into J plus 1, where B is dependent on the moment of inertia, which is mu r square. So these energy levels are specific to a particular molecule, and therefore this infrared spectrum of any molecule can be considered as a fingerprint of that molecule. Okay, I will just tell one more thing. Now, you have, as I said, it is a fingerprint, right? You must be knowing what are isotopes. What are isotopes? Isotopes are elements with the same atomic number but different mass number. For example, if you think of hydrogen, we know hydrogen is 1, 1. This is the atomic number, and this is the mass number in the sense that hydrogen has only one proton in its nucleus. But hydrogen has other isotopes. This is called deuterium, this is called tritium, and the difference is that this hydrogen has one proton and one neutron in its nucleus. This hydrogen has two protons and, it has two neutrons and one proton. So the proton number doesn't change, but the neutron number is changing. So these isotopes are chemically they are identical because the electron number, chemical properties are decided by the atomic number. But if you see the vibrational spectrum, the infrared vibrational spectrum of these molecules, such molecules, you have many such isotopes, and if you have them in molecular state, and if they have a vibrational rotational spectrum, then it would be different for each isotope, because the mass is going to change for each one of them. And therefore this is one very important method by which isotopes are actually, the spectroscopy is also studied. Now, we thought that these molecules, we just saw we saw a molecule with two atoms for simplicity. So this molecule can only vibrate in one manner. But you consider some other molecule, for example, say H2O, which has 3 atoms. Then larger the number of atoms, larger the number of bonds that are formed in the molecule, and therefore more would be the ways in which the vibration can take place. So in the next class, we would study more about these, what are the kinds of vibrations, fundamental modes of vibration a molecule with n atoms can have, and how that becomes important when we study our CO2 laser properties, functioning, etc. So in today's lecture, you have studied about vibrational rotational transitions, and how they happen, how they occur, and what are the selection rules for vibrational transitions, for rotational transitions. I hope you have understood.